Okay, so hi everyone. Unfortunately, there was a slight glitch of a couple of minutes in which the mic didn't work. So I'm going to just redo the 5 or 10 minutes that were lost in class. And afterwards, the recording will continue from the class itself. Good. So at class, we started to talk about free independence. And I started to give the definition. I'm not going to repeat it because we just did it. And we saw the first part of the definition, the main part. And there are a couple of follow-up parts to the definition. So let me just quickly go through them. Nothing very interesting, but say you have a set xi or sets xi, or capitalize an index set, and not necessarily subalgebras. Then we say that these sets are freely independent or free if the subalgebras they generate, the unital subalgebra that they generate, are freely independent in the definition that we had in item 1. Okay, so this is just a way of talking about sets being independent or freely independent rather than the subalgebra generated by them or subalgebras in general. And it's the obvious thing that you will do, just a matter of notation. And in particular, if you have sets of singletons, so capital Xi is the singleton of small ai, then if the subalgebra generated by AI and 1, so the unital subalgebra, are freely independent in the sense of the first item, then we call the AIs freely independent random variables. Right, so it makes sense. So we want to talk about random variables, not subalgebras in general, but really to say that A and B are freely independent is to say that the subalgebra generated by 1A and 1B are freely independent. Nothing to it. And also, if you are in the situation of star probability spaces, then what you require for the AIs, the random variables, to be star freely independent is that the corresponding star algebras are freely independent. Namely, A and B are going to be star freely independent, but we are just going to say freely independent usually if we have the context of star probability spaces. If the algebra generated by 1A, A star, and the algebra generated by 1B and B star are freely independent. Okay, good. And we'll stop saying freely independent all the time, and we're just going to say free, okay? So A and B are free, rather than freely independent. Good. So as I said, maybe we'll go back to the actual definition. The part 1 of the definition is maybe kind of disappointing because it doesn't tell you in an explicit way how to compute the joint moment of random variables which are free. It just tells you that if you will take free independent random variables, so that's actually the definition, right? But it will tell you that if you take random variables that are, first of all, centered, well, that's not a big deal. You can kind of center them. And secondly, so actually I should point to this. They are coming from, there are no consecutive algebras, no consecutive elements coming from the same algebras. Then something happens, phi of that product is 0. So it doesn't explicitly tells you how to compute joint moments, compare it to the tensor case. In the tensor case, you have that if you have, something like that, and A and B are tensor independent. Actually, that's going to be the definition of tensor independence in terms of moments. Then there is a rule. The rule tells you count how many A's you have, let's add a B here, how many B's you have. Now it's 3 and 4, and then the answer would be this thing. It's a very simple algorithm. Here it's not like that. Here, freely independent is defined in a kind of a roundabout way, and the question you should ask yourself is kind of what's the rule? If I'm looking at a specific moment, maybe this A, B, A, B, B, A, B, what is this? I know that, is it the case? And yes. that phi of this word, namely this joint moment, can be expressed in terms of the phis of A's and phis of B's, and how, like what's the expression? Here the expression is very simple. So the next lemma tells you that um, conceptually speaking, rather than computationally speaking, there is enough information in the definition of freeness to give you a formula. But the formula is difficult to look at. It's like it's complicated. Much of what we will do will be to understand the combinatorics behind the formula. But what this lemma tells you is that there is a formula, or there is an algorithm, if you will, that tells you how to compute joint moments from marginal moments. So let's go through this lemma and for its proof, and the proof is kind of explicit. It's a way it gives you a way of finding the joint moment, and in the examples that we'll look at next, which were actually recorded, well enough in the live class, we will use that idea behind the proof. It's a very simple idea. Okay, so what does the lemma tell us? It tells us that say you have a non-commutative probability space, you can take it to star probability spaces also, and say that you have unital subalgebras that are free, okay? And let's look at B, which is the algebra generated by these subalgebras. So it may be not all of A, but it's the smallest algebra that contains all the AIs. Then really saying that there is a rule of computing joint moments for marginal moments in terms of phi translates to this sentence, namely phi, which is actually a global thing, it comes from A, right? It's larger than the AIs and B, but phi, when you restrict it to B, is uniquely determined by the phi restricted to the different AIs. Right? Put differently, you can restore the joint moments, because joint moments are evaluation of this function, joint moments of the AIs, by knowing only the marginal moments. Yeah. So that's what it says. It's uniquely determined. It is determined and it's uniquely determined. Good. So how do we prove that? Well, the proof is an reduction on K, where K is the number of products in the moment you care about. So again, we have A1 up to AK. Each AJ comes from some subalgebra, some subalgebra that we are going to denote by IJ. So IJ is in this index at I, this ambient index at I. And what we want to show is how to compute phi B of this product given only information, given only by applying only phi on the subalgebra's AI, right? Which is the same thing as saying that we are only evaluating these projections. Okay, when K equals 1, the task is trivial because phi of A1 is indeed phi, like phi of A1 is indeed phi of the star algebra, the subalgebra corresponding to this index, the only index here at A1. So good, so we only used, the projected phis to the AIs in order to figure out a kind of a nullified product in a sense. But let's assume K is larger than 1. And we are going to, as I said, we are going to prove the things by induction. And we are going to assume, and it's without loss of generality, that actually consecutive indices are different. Why? Because if you are giving me A1 up to AK, and maybe A1 and A2 came from the same algebra, then you can just go ahead and look at A1, A2 as one element in the algebra, in the common algebra. That only reduces K. So the induction, doing this assumption within the induction is still valid. And you can repeat that K is finite until you get to a situation in which this holds. Right, so it's okay to assume that. But we can't assume that things are centered, right? Because maybe A1 is not centered. If all of them are centers, the product is zero. So actually, we are going to use that in order to figure out a formula for A1, for phi of A1 up to AK. And the way to do so is to actually center the AIs, or AJs. So for any J between 1 to K, we are defining this AJ. So it's not AJ to the 0, which is 1, just a notation. AJ centered to be AJ minus the expectation of AJ according to the corresponding phi. So this is phi, but it's also phi restricted to AIJ, right? So it's you can use this projection. All right, so what happens, what this does is really, centering things, right? Because the expectation of AJ0 is going to be 0. Phi of AJ0 is going to be 0 because phi of this thing is 0. And why do we do that? Because now we can write A1 times AK as this product, where we replace A1 with A1 centered plus phi of A1 and so forth. I mean, we did nothing by doing that. But now when we open up the parentheses and use the linearity, the fact that phi is linear, we can see that one of the 2 to the k summands is going to be phi of A1 0 up to AK 0, which is 0 because of freeness, right? Because the AIs are coming from algebras which are different algebras are consecutive algebras are different, and also their centers, right? Because if an element is an algebra, centering it keeps it in that algebra. You just subtract a complex number. So each of them is centered, and we have this condition, and so right, and we are, and therefore by the definition of freeness, this thing is 0. And then there are the remaining 2 to the k minus 1 terms. So let's look at them. I call it rest, and I'm expanding rest here. So rest is going to be a sum. Like in the commutative case, you would just go over all possible subsets of size k, maybe other than the empty set or whatever corresponding to the one summand that was turned out to be 0. But here you need to be slightly more careful because things are non-commutative. And so when you take the products and you choose from parentheses, who do you want to take, you need to make sure you maintain the order of the products. So the way to do so is like, rest is going to be a sum, and the sum is going to be indexed by, well, first of all, I guess by a number S, but then by 2 vectors, P1 smaller than P2 smaller than PS, and Q1 smaller than Q2 smaller than Q. A minus S, where the PIs and the QIs, ignoring the order, is just a disjoint union of K. The PIs are going to tell you in which of the parentheses you took the variable, the centered variable, and the QI will tell you if you took the phi of that variable. It's just a number. Right, so for example, if P1 is 1, here you take this, and if Q1 is 1, you take this. If P1 is 5, it means that in the first 4 parentheses, you chose you chose the fees. Okay. So it's a way of kind of a bookkeeping of the different summands. And S is, you should sum over S also, and S is the number of parentheses from which you take the variable, the centered variable, rather than the minus phi of that thing. Right, so I'm going over all S's. Let me keep this open for a second. What is the minimal and maximal S? The PIs are going to be to encode the parentheses from which you chose the centered variables, and the QIs are the remaining parentheses. And now if you think about it, an element is going to be phi of, well, either AP10 or phi of AQ1, depending on whether P1 or Q1 is smaller, which of them is 1, and so forth. It's kind of a mess. The nice thing is that the Q1s, when you look at the parentheses in which it's a Q parenthesis, and then you take the number rather than the variable, then it's just going to slide outside of phi. Right? All the Q's are actually going to slide out because these are just numbers. So what will happen is that we'll get this expression up to -1 to the k minus s, which I forgot, but never mind. This expression, because right, you have these parentheses, all the products, all the parentheses corresponding to the Q's, you're just choosing within the phi a phi, right? So it's this thing. Within this phi, you choose the phis. And the phis will just, these are numbers, they will slide outside. Right. I don't need that, actually, that's fine. And therefore you can write it kind of very compactly as the product of the phis corresponding to the Q's times phi, this thing of, and now you should be careful about the order, the centered element indexed by the PIs. Now the point is that, S, what is S? S is the number of parentheses from which you take the variables. And my point is that S can be 0. Maybe you take only the numbers, not the variables, but it cannot be K. It's at most K minus 1 because you already considered here, outside here, which is 0, you considered already the choice of parentheses in which you take the centered variables, all of them centered variables. So S equals K. So we know that S is at most K. And that calls for induction, of course. Right? Because now what you can do is you can say, well, these things are fine. These are phis that I want to see there in my expression for phi of the product, because these are the phis that are evaluated marginally on the AIs. This thing is not, but it's the same problem as we had before, but now on size is S, which is at most K minus 1. So you can use induction to open this thing also as a sum like that, and then again and again and again, and so forth. Good. Yes. So, by the way, note that at the first sight you may think that maybe this is also 0 because you have a product of centered elements, but that's not the case because maybe, I mean, these are product of centered elements, but maybe P1 and P2 are equal because maybe P1 is 1 and P2 is 5. And so AP1 times AP5, sorry, AP1 centered times AP5 centered may not be centered, right? Even maybe these are the same elements even. So the fact that an element is centered doesn't mean that its second moment is 0 as well. So this is not 0. If this would have been 0, everything would have been 0. It would have been weird. But this is smaller in terms of the number of products that you have, number of terms that you have in the product. So you can use induction and get a result. Okay. Another, as I said, this operation, which we'll do quite a lot, is called centering. Good. Now in the real life class, I actually considered several examples, but I think that the first very simple example was missed because of the audio failure. So let me just do it here. So this is a very simple example. Let's assume that A and B are free, which again means that the algebra generated by them, 1A and 1B are free as subalgebras. Then I claim that phi of AB is phi of A, phi of B. Okay, like in the tensor case. So how do you see that? So the trick is to use the proof, essentially, of the previous lemma. So you want to understand phi of AB. So the first thing you do, you center A and you center B. So you subtract phi of A and phi of B respectively, take the product, and you know that this is 0, first of all. Because A and B are free, and so in particular, so A and B are free, which means that the subalgebra generated by A and B are free. This is an element in the subalgebra, this is an element in the subalgebra, because phi of A is just phi of A times 1. And so A minus phi A and B minus phi B are free. they're centered, and so by the definition of freeness, this is 0. Now, 1 second. Yes. Now you can open this up, which is essentially what we did in the proof and used induction, but now it's just, there's no need for induction. We are very close to the base case anyhow. So when you open this up, you get within the parenthesis of phi, right? You get, so there is a phi of, and then you have AB because of these two. And then you have A times minus phi of B because the same A, but this one. And then you have plus minus phi of A times B. And then you have two minuses, but okay, let's do a plus phi of A, phi of B. And now when you use the linearity of phi, then phi of AB is this thing. And the remaining terms are what? So you have phi of A times this constant, which is minus phi of B. So minus phi of B slides outside, and you get phi of A times minus phi of B. And same here. And same here, but with a plus. This is kind of different because now this is a phi of a number or a product of numbers. Here it's a phi of a number times an element, but the number slides outside, so eventually you get the same answer. Anyhow, you get the phi of AB that you cared about, and then you get the same expression 3 times, twice with a minus, once with a plus. So you're ending up with one minus. So you get that 0 is phi of AB minus phi of A, phi of B. And so phi of AB is phi of A, phi of B. In the live class that you will see in the next video, we did more interesting examples, but you should just wait to see them there. Okay. Hopefully next time we won't have these glitches.